In the last part of the video, I'd like to introduce uh, the tasks we would like to explore in our lab study in week 3. Uh, Please not try to follow everything in details, especially in the 2 hours lab session. Take it as an example of practical data analytic project. I hope that would be helpful for your course projects. Let us have a look. The job in this task is to build an email classifier to distinguish real messages from the spam the messages contains false or whatever advertisement information. To do this, we train the decision tree model on a group of emails that has already been labeled as good or spam messages, and we will pre-process the email message into some more manageable, mathematically manageable objects for our decision tree model to process. And we'd like to evaluate the model and have a look at its performance. So the first thing we need to do is to farm this utility. I wrote this import a functionality called load email data. Notice that this part of the code loads the training data that's been provided with this lab code. It is dealing with the training data. Okay, and the usage of function is quite easy. In a list, which we call the sources, of email corpus, in each of the corpus there is a path to the subdirectory containing the email and the tag on this group of messages. I don't know where the tradition comes from, but we call good messages ham and the bad messages spam. And now, in our case, I put everything in a subdirectory called email data. And in this directory, I have two subdirectories. One is called ham, and in the ham, I have a structure, but in each of the subfolders are email text files with real good message. And there is another subdirectory called spam, and in each of these contains spam messages. After we run this image loading function, the images will be put in an object called data. Data is of the type of a data frame. If you are an R user, this kind of data container would be familiar to you. So let us have a look at the code here to have a deeper understanding of what is going on. The load email data function is defined at the end of the utility Python file. So I put data in, I create a data frame, and data frame is being imported from this called pandas package. Pandas package is packages that do similar functions as NumPy, but it's more it is better at dealing with data with heterogeneous structures, such as text or different kind of databases. And the data format called DataFrame provided by pandas can be easily transformed from and to NumPy arrays. So I create a data frame, and from the email source list, I read the messages and insert the loaded email message into this data frame. And the last part is to shuffle the data a little bit so we can easily split it using into training and test part of the data set. But this part can also be done in later in NumPy, so this doesn't matter very much. Have a look at the actual function called build data frame that load email data from a specific path and attach the tag ham or spam to the email data that's been loaded. This function is defined above build data frame, and the build data frame is again rely on this function called read files. The read files working through all possible independent files in a directory and load the text content of the files and put the text into the rows of the data frame and attach a tag of ham or spam to that sample, which is a row in the data frame. So have a look at the data. In each of the group, we have subfolders, and in the subfolders, there may be multiple layers, multiple structures in the subfolders, but eventually we will arrive at some seemingly random data file names. And if we open the files, okay, we can just drag it into the text editor. There are plain text, not completely plain text files, they are formatted email messages. Okay, let's close this. Oh, yes. So let's have a look at the read files from a path. And in this function, we use this particular function provided by the OS operating system module of Python. It gives you an easy way to exhaust and to iterate over each items in the path. And look, our condition is our processing is that if the item itself a subfolder of the folder, treat it as a folder and call the function itself again, so we can go through the whole structure of a folder recursively. And if the file is well, not a directory, it's a normal file, we consider it's a text file. So we load the text file and read the content of the file for each line in those file. We read the lines and put the content into one big chunk of text, and then return. Look at this keyword of Python, yield. You can consider it as return, but we can understand, add a word to that. We can understand as lazily return. That means when the returned value is required, actually accessed, the entire function is getting move one step forward and do a return. It does not go everything, go every step and return again and again and again. It returns only on demand. So call it lazily return. And return the path of the file and the content of the file. And for the content, we need a little bit more processing. That is because, remember, the the emails are not completely plain text. It contains some formatting information like the font, the sections of an HTML file. So this part, strip text, is well, obviously strip HTML text from the text. It is implemented plainly using an HTML parser. Here we use defined function. Here we create an object. That object is a subclass, which is a class that has inherit many all of the functionalities, method, attributes of an HTML parser. An HTML parser is a functionality provided by Python. Note that here there is a difference between Python 2 and Python 3 in this operation. So when you use this function, if you are using Python 3, please do the operation here. Comment out these 2 lines of code and enable this one. If you are using Python 2, using this part of the section. Okay, so this is the code dealing reading email data. To deal with the text, look, a text is a variable length body of data. That is, even for a single data sample, its length is the memory takes in the computer is not fixed, so it is not very mathematically accessible. For the data model to process the data has to be of some certain form, so that we can build models and do processing about the data. One common way of dealing with the text data is to consider the content of the text, the statistic aspect of the content of the text. To be more specific, here, if the data, sorry about this part, quickly, if we use this head means take the first n samples from the data frame, and we can have a look. The pandas data frame provides more human accessible format of the data than a simple NumPy array, and that is because the nature it is dealing with more structured data. Okay, the first samples contains this. The class are, well, in this case, all spam, and the text content of the data is like this. This backslash n means a new line. It doesn't matter here. Okay, to deal with the text data, we first need to format data into some mathematical object. And to do this, we will use a feature builder called count vectorizer. That means we vectorize the dataset. Each of the sample will be transformed into a vector of a certain length. And for example, if the vector is of 10 dimensions, that means we are concerned with only 10 words of all the text. And the feature of a text body will be the statistics of that text with respect to the 10 words of interest. That means we count how many words the text contains and count only with the text we are interested in. So to build such an this function, if you need to implement it, it could be a little bit complicated for you. Scikit-learn provides a convenient implementation of this functionality, and it is located in the feature extraction submodule, and especially for text data. The name of the class is count vectorizer. We can create such an object. For example, we can let the counting is to count words. I think we have different choices like to count letters, different kind of codes. But now, for email data, word is an appropriate choice of the basic unit for counting. And the stop words means some words that is too common or too rare, generally too common in English, that it does not convey very much meaning of the content of the text, such as words like of, that, or this, for. Those words, when you are presented with such the information that some text contains a lot of words of generally this won't give you much hint about what the text is about. That makes sense. And the max features is to determine how many words you will build for such a text data. That is the vocabulary we just talked about. Like if you want each of the text body is converted to a 10-dimensional vector, you can give 10 to this parameter, to this argument. If of course 10 is a little bit too small for general English text, and here I use 60,000. It's a little bit big, but we didn't take the trouble of differentiate different forms of word, like work or worked, or different forms of B, M, is, R. They are counted differently, so we need a little bit large number here, but that is not a good practice. To build a practical text analyzer, we'd better to let the model at least be aware of different forms of words, right? And that is ngram. Ngram means the granularity of the word counting, such as if we count only single words, is what we are using here. The minimum number of words in a counting unit is 1, and the maximum is also 1, so it counts only single words. If we'd like, we can let it count 2-word units, such as text analyzer, count vectorizer, United States. Those can be counted as a single text unit, and we can also put 3 words, 4 words, so on and so forth. The token pattern, I'm a little bit sure that this should be the default value. We shouldn't worry too much about that. That means the word consists with Latin letters, and the Latin letters are from A to Z, from capital A to capital Z, and they need to be linked together with at least one number. If you are curious about this construction of the format, you need to have a look at a term called regular expression. This is regular expression representation of a text pattern. Okay. In the next statement, we use this count vectorizer fit and transform the data. So fit and transform means to construct the dictionary and use that dictionary to transform the data provided into vectors. And this is the way of accessing the data stored in the data frame. I would not elaborate here, so if you are interested, you are not very comfortable with this data accessing mechanism, you can refer to document of DataFrame of the pandas package. Data is pandas.dataframe object. Okay, let's have a look at this transformation first. We can give a more simple example that is more accessible to us to discuss and check its functionality. We copy this statement and use it to transform some simple text, such as, let us use it to transform maybe only 2 lines of text. Let's use a silly text such as a fox was jumping jumped over a box where her sister fox was hiding from an ox looking for a fox in a box. Well, this is silly, but it can pretty much give us example of how this function works. Maybe the second sentence lesson, foxes are good at thinking out of box. Well, yeah, kind of silly text. Let's use this to transform it. Let's check the result. Print. Can't vectorize vocabulary. We use this one with the underscore to check its internal attribute of the vocabulary. And also let us print the constraint. Okay. So the vocabulary, non-surprisingly, contains box. Box is in the index 0, which is the first entry of the vocabulary. Look, the entries are not ordered as their indexes. That is because when we construct such an object, generally not all the text contains all the words. So the representation of this form of data is generally in the form of a sparse matrix. In a sparse matrix, we store the entries of non-zero numbers, and this vocabulary is also stored in a different object called dictionary in Python, and the order of the entries in dictionary does not matter. So let's check. Anyway, let's have a look. The first is box, the second is fox, and okay, a nice is sister, so on and so forth. And have a look at the data. The first row of the data represent the first sentence in the text body, and the first sentence has such many non-zero entries. The 0 and 0, that means the first row's first column contains 2, and the first column of the first row represents 2 box. That means in the first sentence there are 2 appearances of the word box, which is as expected over a box and in a box. And in the first row, and the second entry, there is a 3. That means there are 3 appearances of the word fox. So let's look. Yes, a fox, second fox, other fox. That is good. Notice that this trivial transformation treat fox and foxes as 2 words, although it is clever enough to treat capital and lower cases of the letters as the same, but foxes counts another word instead of another form of this word fox. So this will be on the 3rd column of the matrix. And in the first sample, let's check. I don't think there is a single appearance of foxes. So the 3rd column does not appear in the sparse matrix. That means that entry is 0. And on the 2nd row, there is an appearance of foxes. And the appearance is 1. So that is our data. Now the data is ready. I need to remind you that if you follow every step until now, I will suggest you to go to the kernel, restart and clear output, and rerun the steps until this part, because in the previous demonstration, I think I managed to destroy the training data we just built by using the silly fox text. And on the other hand, if your laptop or computer has some limitation, especially when it has limited memory to deal with the entire text data, I would suggest you to, instead of using the entire subdirectory of ham and spam, to use some subfolder in those 2 paths, so we have a smaller data sample to deal with. Okay. And the actual step of building and running the decision trees is, as usual, very simple. After data is ready, we just need to from particular import decision trees. Now, this time we import the tree submodule and use the trees and decision tree classifier to build the decision tree classifier. Note that we need some specification of the decision trees in case we build exceedingly complex and useless model, because there are too many features for the decision trees to use. Look, we have 60,000 features per sample, so we need to limit the complexity of the decision tree a little bit. We put a limitation of the depth of decision tree of 20 questions. It's like a game that after I give you answers to 20 questions, you must arrive some decision. So no matter you are completely certain or not, okay. And there are a little bit different specifications about what is the minimum number of non-leaf node, number of samples a non-leaf node contains. That is to prevent the tree to split the population into a very fine but not very useful portions, and the frictions of the weight in the leaf. And I also put random state, so I would like the algorithm run each time and come back with a certain result, and use the fit function to fit the x part of the data. In this case, would be the training data's count, text count number, and the training data's target value. We arrive with a decision tree, and in this part, we calculate the performance of the tree on the training set, well, this is not very good because you generally would expect something better on text file, on classifying emails than this. But well, this is an example of using decision trees and dealing with text data, so please put up with it. And on the training sample, expected the performance a little bit worse, but similar to the text file. But look, this performance is not very good. Consider this when we are dealing with the text file, emails, you obviously do not want your spam detector to put important messages into the trash folder when those messages arrive automatically for you without letting you know. So probably we would, before we put this classifier into practice, we need to adjust its behavior a little bit. So only when it has really high confidence on that the text really is a spam message, before it can deal with the text automatically for you. So in this case, that is the trading off here. The high confidence in classifying something into spam means low confidence when it is classifying it as a real message. If you directly put this implementation of the classifier into use, approximately it will leave about maybe three spam mails in turn in your inbox. But look, for such a simple implementation of a classifier, you can expect maybe this much. Okay, that is this week's lab tutorial. I hope you can explore and enjoy playing with it.